Hi everyone, my name is Ellissa Verseput and I'm a machine learning engineer at Quby. I hope you all had a great lunch, but are now ready for one of the most exciting talks in the use cases track. Because today I will talk you through how we power homes to get ready for the future. And this is what we'll do today. So I'll first talk you through a little bit about what Quby is, what we do, and how we do it. And basically that sets the context to dive into two use cases that we're currently tackling with Quby. One is about how we make homes more efficient by helping them save energy. And the other one is about how we optimize the current heating program in a smart thermostat. And in that way, not only saving energy, but also being able to make at home more comfortable. So, probably most of you were at the keynote this morning, and my chief data, Stephen, already introduced Quby a little bit, but let me tell you this again. So Quby is a company that is in the smart energy domain, and basically what we envision is that we want to make the world save as much energy as possible. And we do this by trying to make households more sustainable, but keeping it easy and also comfortable in these houses. How do we do that? Basically by having lots of technologies out there and app solutions. So who here in the audience has a smart thermostat installed in their houses? Okay, some hands, good to see, good to see. And are there probably some people who, well, have heard of the smart thermostat Toon, or if you're from Belgium, Box? Good to see some hands as well, great. So this is actually one of our main products. You see it right there. And that is our display solution that we install in houses, and that gathers lots of data from that house in order to give energy insights and to control the heating. Next to that, we have app solutions that either cooperate with this hardware solution, so this display, but also standalone apps that don't need any hardware installed in the houses, and are just able to give energy insights as a standalone app. Next to that, we also have other IoT devices that are either connecting with this display or standalone that are able to serve the households. And basically all the data that is gathered with these hardware and technologies, we are able to develop data-driven services on top of this big data set that we're gathering from it. Some examples here, but we're going to dive into some later. So how does, for instance, this smart thermostat, this display we install in houses actually work? So this display is connected to basically two core components. One you see in the right top, and it's connected to the boiler via the boiler adapter. In that way, we are able to control the heating and also get all kinds of data from the boiler that we can analyze and also develop services upon. Here, on the left side, we see that this smart thermostat is not just a smart thermostat controlling the heating, but is also connected to other sensors in the home. So we basically measure water, gas, and electricity, either via a digital or an analog meter. And next to that, we are also hooked up to all kinds of other data sources in your house that are interesting in this energy context, like solar panels, your IoT devices, smart plugs, and so on. And this, as Quby, we don't do alone, directly to the end user, the households, but we cooperate with energy providers, utility companies, in different countries in Europe. So we started out in the Netherlands, cooperating with Eneco, but from there, we took it to Belgium, Spain, and we are also experimenting, or actually running our first pilots in Germany. And in each country, we try to cooperate with one of the biggest utility companies. And this already gave us more than 400,000 connected homes with such a smart display in these houses. And you can imagine if you sample all these sensors most of them every 10 seconds, for all these households, that's generating terabytes of data per day. And actually, this distribution among Europe also makes us one of the biggest smart thermostat companies in Europe. Next to cooperating with utility companies, we also cooperate with other partners like water companies and insurances and banks, because these people are also having a say in how we can save energy in the homes. So, that's it for a bit of introduction about Quby and setting a bit of context. So now you know how we are gathering data and what kind of devices we have. So let's see what we can actually do with this data in order to make the people in the households more sustainable while keeping their level of comfort at the same level or even higher. So first, the bill breakdown use case. Excuse me. No, before we dive into the bill breakdown use case, let me just give you a short overview of basically all the data-driven services we have at Quby. We like to divide them in 3 different domains. And also at Quby, we work with domain teams we call value streams on these different topics. So some of our services we purely see as efficient home services. They just make the home more efficient. Other services are making the home more comfortable, and others are making it more trusted and more safe. And today we'll dive into a use case for the efficient home, energy insights, a bill breakdown use case, but we will also look after that into a comfortable home use case, because we will look how we can optimize the heating schedule so that it's on and off at the right times. Okay, now we really go into the efficient home use case, and this is about bill breakdown. So I guess all of you every month get an energy bill and just see how much euros you spend on either your electricity and your gas. But the service that we created is actually making a deep dive on this energy bill. And we are able to provide the user in their app with a detailed breakdown of the different appliances of your bill. So how exactly each appliance contributed to your monthly energy bill. And we are also able to take this to a different aggregate. So we can also see it on a weekly basis, a yearly basis, and so on. So how are we actually doing that? The key technology to it is load disaggregation. And what do I mean with that? Load disaggregation actually means that we take an aggregate signal, so in this case, the pure electricity signal coming from the electricity meter in the houses. And this signal we're going to divide up in its different components. So which part comes from the washing machine, which part comes from the dishwasher, and so on. And if we look at the electricity signal for a day for somebody's house, that can look like this. So when we do load disaggregation, we're going to define in this signal which part is actually caused by which appliance. So for instance, we are able to see a washing machine, a dryer, and when the dishwasher is on. And notice that this electricity signal is actually quite detailed. We get it because we have this hardware installed in the homes, the smart thermostat, every 10 seconds. So there is a lot of detail in the data. We can see all the ups and the downs, and therefore we can see the typical signatures. Also, a little bit, just by looking at this signal, you can see that there is a particular signature in the data for a washing machine or a dishwasher. And if we know from this aggregate electricity signal which part was contributed by which appliance, we are also able to split up that total electricity usage in its different components. And in that way, we are able to see all the different appliances and basically work it out in a accurate bill breakdown where all the components get its own costs associated with it. So that is the case when we have this smart thermostat, this display installed in these houses, and we are gathering the data every 10 seconds. Now, I also told you at the beginning that Quby is also having solutions or having data services for people who don't have such hardware installed in their houses. Because, for instance, in the Netherlands, already more than half of the households have a smart meter. And the smart meter data is, can be gathered just without extra hardware in the houses. But this data is not coming in every 10 seconds. It's not measured every 10 seconds. We only see it with a 15-minute resolution. So that's a lot lower resolution than the data we're gathering with the smart thermostat. And here you can actually see the difference. Now you see that this data is basically having a lot less detail, and you don't really see it anymore where exactly are the ups and the downs from my washing machine. So you can also imagine that for machine learning or AI, it's also a lot harder to identify which components in this aggregate electricity signal are actually accounted for by which appliance. However, the goal at Quby still was to give a bill breakdown in different components. So we still want to give a bill breakdown where we can say, okay, this part of your energy usage goes to white goods, this is for cooling, and so on and so on. And we found a solution to that problem. And the key here is actually very similar to a problem we see in image recognition. And you probably all have seen super resolution algorithms where you can train a model on a lot of examples with low resolution images and its high resolution counterpart. And after you've trained the model with a lot of these examples, it is able to upsample a lower resolution image. Now, we are actually doing the same thing at Quby. So we found a method where we can actually upsample the lower resolution data to higher resolution data. How does this work? Well, we have our user without a smart thermostat, only the smart meter with 50-minute data in their houses, with 50-minute data resolution, 50-minute resolution data. And what we do is we analyze this signal for a day, and we can do some very basic appliance detections. For instance, you can see what is the minimum level of energy usage that is always used in the house. We call that standby. Or we can see what is accounted for by the fridge. But there, it almost stops. So now we need a smart technology that is able to upsample our data so that we can also see the other appliances. Now what we do, we have an AI that is able to look at our smart thermostat users, this 400,000 user base, and look at the high resolution data from these users, and in a smart way match the low resolution data against the high resolution data users and find the most similar user. And in that way, basically enhance the very basic appliance detections we are able to do for the low resolution user. And in that way, we can still give this user, where we only gather the low resolution data for, a bill breakdown where we give his energy usage split up in the different components. So then the total picture, how did we implement this at Quby? So let's start here at the bottom. We have data coming in from our smart thermostat clients. So this is the high resolution data. And we basically, so this is coming in because we also give these people the high resolution bill breakdown. But also, via a third party, we gather the data from the smart meters, the 50-minute resolution data. And all this data is stored in S3 and via the Hive Metastore comes into our Databricks platform. And there, of course, otherwise I wouldn't be standing here today, we highly rely on Spark for running our data pipelines and basically running this algorithm stack that I just explained, both for the smart thermostat users, so the users with a high resolution, in order to provide a bill breakdown in the app, but also to do the upsampling for the lower resolution people and also give them a detailed bill breakdown. So to sum up this use case, basically the thing that we achieved is to go from just this signal, which has not much detail, we are actually able to give an electricity bill breakdown in all the different components. And I didn't explain it in my previous slides, but we're actually, with a similar technique, also able to do this for the gas. So we're covering both energy usage bill breakdowns. So that's it for the first use case, for the efficient home. I hope you guys are still with me and not brain fried yet. especially after the nice lunch, not the lunch dip. So hang on in your seats, and we're going to the next use case, because I also would like to tell you a bit more about what we did with our thermostat program advice. Now, thermostat program advice is a feature that is actually only for the users with a smart thermostat in their homes. I mean, you can imagine this. Because it's actually advising how you should better use your smart thermostat. The smart thermostat has a heating program configured for each user, and you can basically set it yourself to your preferences. So you can set when you are away and when you are home, and what temperatures you want in your home when you are in these states. Now, this feature should advise you on mutations on your current schedule in order to match your behavior in a better way. So the goal is here to basically observe from our smart thermostat users what is their behavior and how does it differ from their current heating program, and can we basically advise them on how to better use their schedule. Now, the key technology to this is that we need to be able to identify the behavior of our users of the smart thermostat. So, are we able, from all the signals that we are gathering with the smart thermostat, the gas, the electricity, the water, name it, are we able to basically determine when is he typically present or not? What is his behavior? And this is actually, with the smart thermostat, a nice task because we do this in a non-intrusive way. So basically the task is to just basically observe this behavior in a non-intrusive way, so only from the data we are already gathering with the smart thermostat, and not by installing a video camera or motion sensors or these kind of things. And actually we claim that we are able, with the smart thermostat data, to have a proof of life, so to see if somebody is present or not in the home. And also that this goes actually further to more use cases, so we can also look for safety in the house. Is somebody active or inactive when he normally is? And we can optimize heating and lighting, because we can suggest a better way of when to turn on your heating or when to turn on your lights. So this was the challenge we faced with the data team, because in order to provide this feature in the app, we needed to create a model that is able to do the presence detection in order to determine the behavior, the general behavior of the user. So basically we started out with the raw electricity and gas and name it data, but of course we had some, in this case, good legacy, because we already have a stack of AI algorithms and domain signal processing algorithms that are able to detect all the different appliances when they are on. So you can imagine that we also wanted to try these kind of already detected events as features for our presence detection. But then the next challenge was that we actually don't directly observe with our smart thermostats if somebody is home or not. I mean, that's just not a variable that we observe. So we didn't have a training set to start training our model on. Which features determine if somebody is home or not? So what we did is we actually started a survey with some test users, and for a couple of weeks, we asked them to, for the previous day, fill in when they were home or not during that day. And that basically gave us a training data set to start our experiment, to start our modeling. So with the whole data team, we were super excited. And of course, then we got into this challenge where a lot of data teams face themselves in when you work with a lot of people on the same model, and you're going to try out a lot of different things, and in the end, you need to reproduce what are actually the decisions, and why did I make them, and why is now my current model in production, and why. So basically, the challenge is we want to track model improvements and reproduce the models. So, I mean, you might have already been hearing about it on this conference, but a nice solution proposed by Databricks is MLflow. And since a little bit less than a year, we started using this, and we also heavily relied on it with this project. So basically we started working with MLflow in order to try our different models, try which features were working out for us, and basically what model we wanted to first try in production. Now, I don't think this is the right presentation to go in the ins and outs of MLflow, because there's plenty of talks you can go through to see more details of MLflow. But just in case, who has used MLflow before? I'm wondering. Okay, so actually it's great because I also see a lot of people who don't raise their hands. Because if you haven't used it before, it can start as simple as this. So if you have your standard Python code, where you, for instance, with a sklearn model, first divide your training set in train and test, then start your first pipeline, where you select your feature columns you want to try, have your imputer, have your model that you want to try, then fit it, after which you predict on your test set and calculate some metrics. Okay, that is what you regularly do if you don't have MLflow. Now, just, you can, in Databricks at least, start as easy using MLflow by just adding MLflow.start run, which starts up an experiment in the background that is able to track your models and compare them later on. And after you've done your model fitting and your metric calculation, you can start logging the parameters, the metrics you're interested in. And also, Databricks really nicely incorporated a view in your notebook where you can actually, in the same notebook, also track the different models you've tried, compare the different metrics. Now, this is a really basic example, but I mean, you get it. This is actually really nice to try out, so I can recommend it to all of you if you haven't used it yet. Now, we were done with MLflow. We thought, okay, this model is the best one, and we know why it is so because we have tracked it through history or through like our developments. But we worked with Python because Python is a nice language to develop machine learning algorithms with. But now we want to bring our model to production. And at Quby, we like to use Spark Scala in our production pipelines because, for instance, of the dataset API, you get a lot nicer testing and type safety easier with that than with Python. So how are we going to solve this problem? So imagine that at Quby we have, this is an abstract idea of how we run all our jobs after each other in parallel and in sequence. And now suddenly we have, at some stage in one job, we have a data frame, and for this data frame we want to predict if somebody is, or actually we want to predict if somebody is present or not. Then the solution we found was actually to use just the Python model, but wrap it in a pandas UDF. So I'm going to explain to you in a bit how exactly we did that, but I just want to take the liberty here to mention that because I saw this nice koala logo here at the conference, I thought, oh, I also want to create such a cute logo. So I took the liberty to design my own logo for this particular way of working. I hope you like it and are not offended as a pandas fan. Anyways, so a pandas UDF is basically a optimized way of using the row by row UDF we all know from Spark, because it works in, it processes the data in batch. But basically, if we are in our Python cell and we have our safe model, and we load it from storage, we can wrap it in a pandas UDF and register it at the current Spark context. Now, in our Scala cell, in the next one, we can, where we use the same Spark context, we can simply call this UDF and still work with our trained Python model, without all the hassle of having to either transfer the Python model to Scala or basically bring our pipeline to Python. So pretty elegant, I would say. So then again, the complete picture. Because remember, the goal was, after this whole data modeling phase, to serve our users in the app a program advice in order to optimize their heating schedule. So we had our survey with our test users, from which we collected when they were home or not, coming into our S3 buckets. And we also have all the data coming in from the smart thermostats. We run all our pipelines, including all the algorithms we already have for the appliance detections and these kind of algorithms. But now, on top of that, we have actually as a sidetrack the MLflow experiment, and by that the saved model wrapped in a pandas UDF, and a new pipeline that basically gets the right feature columns in a data frame and is then able to call the pandas UDF in order to do the presence prediction. Now, once that is done, from this presence predictions, we can actually see the typical behavior of a user and, based on that, compare that to his current heating schedule and advise him on the best mutations he can do now in order to save on energy and have his schedule on and off on the right moments. So, what's next? Because this is actually a use case that's not standalone. We are now able to identify the behavior of a user with a model. What else can we do with that? Well, for instance, the vision at Quby we have is that we can go further with this. Because imagine that from this behavior tracking, we are able to assist people in their houses, that we are able to see when your son came home, or when your grandma, if she has had her cup of coffee in the morning and she's all right. Imagine that you can actually assist people in their houses without having to, well, basically do that in a non-intrusive manner. That's a pretty cool use case, I would say. So, that was the second use case. And by that, we're also coming almost to the end of my talk. So I hope you now all understand a bit of the ins and outs of Quby, how we do stuff, and how we do that exactly. And we covered two use cases. One, how we make homes more efficient by giving them energy insights, and one where we optimize the heating schedule. So I hope that you now get some great inspiration from that, and also want to contribute to power the homes from the future. This is the bunch of people we do that with at Quby. And this is my business card. I think this is the right time for questions. And if you see opportunities for cooperation, also please mention it, because I think this is a really interesting industry, and we are preparing here for the future. Thank you.
So we've got time for questions. I'm going to take the left-hand side of the room. If you just raise your hand, and we'll bring the mic round.
Oh, wait a second.
Yeah, wait for the mic.
Thanks a lot for this talk. It was very inspiring. I have one question about the super resolution. I found it an interesting approach. Do you know anything about the performance for your situation? How did it really do? Or do you have like the ground truth somehow to see if it's really doing the resolution right?
Yeah, so here the ground truth is kind of hard to observe. So what we always do is we compare it against the bill breakdown we have for the high resolution clients. So of course it's doing a little bit worse, but what we also do is we compare it to the competitors. And what we see is that we are actually in this market, well, at least as good or even better as our market competitors in this. But an exact number I don't have for you right now. Maybe one of my colleagues has it for you if you're really interested, but I hope it answers your question a little bit.
Okay, thank you.
Got some more at the back.
Thank you for the talk from my side as well. Very interesting. One question, can you tell a bit more about the algorithm for their appliance detection? What's the logic behind? Which technology are you using?
Mm-hmm. Yeah, so I think it's easier if I take the picture. So, whole way back. So, this one you mean, right?
Yes, correct.
Yeah. So, yeah, actually for all the appliances it's a bit different. For some of the appliances we actually use really domain signal processing. So for instance, if you look at this washing machine, you can really see a typical washing machine behavior. You always have this heat-up period of the water, after which you go into just turning around your washing machine and turning around the clothes. You can actually really recognize that here from the signal. So you can imagine that a signal processing algorithm is able to detect basically these edges and these typical patterns, and in that way, for instance, identify the washing machine. Now, for some of the other appliances, like the dryer, this is a bit harder because the typical usage behavior differs between dryers. So there, for instance, we rely on deep learning. Yeah.
Okay, and how do you handle overlapping appliances?
Yeah. Actually, to be really honest, I'm not 100% sure. So what we do is, like some appliances, they basically always overlap. So like the fridge, for instance. And basically this you can take off from the complete signal, and then you remain with the leftovers. How we do that exactly for the more harder appliances, there I really rely on my colleagues that are experts in that area.
Okay, thank you.
Thanks. So it all starts with the data, and you mentioned here that you sample every 10 seconds. Is this 10 seconds, is there a specific reason behind it? Is it like a because, or is it just something you set for by chance? And now that you're quite a bit down the line, is 10 seconds actually something you want, or could you do with less, or do you need more precision?
So let's start with why we chose 10 seconds. So actually, a lot of the meters in Europe have a so-called P1 signal. That is every 10 seconds or on change by default. So that's actually what we use as well, so that we don't have to. And your second question is?
Yeah, so I was sort of assuming that you choose 10 seconds because of a specific reason, and then my question would now be like, is this something you would actually want, or would you like a higher resolution, or can you do with a much lower one?
I think for these use cases we have right now, this is actually, I'm not sure if we could do with a lot less, but this is detailed enough to do these appliance detections in a good way. But yeah, we didn't really research the limit where to go between 10 seconds and 15 minutes or something where we could maximally go, because yeah, we really don't have this problem actually, because we have all these smart meters around with this P1 meter. Yeah.
All right, thanks.
Do you do any kind of user-specific learning on the appliance detection? Like if a user has a specific dishwasher or whatever?
Definitely we do. So actually for each user we detect these appliances, but that is not per se user-specific, but what we do afterwards with these detections is per user we actually train a model and identify the signature of these appliances for them. So for instance, also for the fridge, we can see if that is one typical signature or even two, so we can identify if you have two fridges, for instance. So these kind of things, yes.
Thanks.
Hello, thank you very much.
Where
I
are
really
you?
enjoyed your discussion.
Oh, hey.
I wanted to ask you a question regarding the pandas UDF you use. We had the same challenge as you had, especially when we have to put machine learning jobs into production. So the way we did it was also using Scala to ensure type safety and so on. But we usually had to code refactor everything to incorporate logs, error handling, etc. But you seem to have another approach with the UDF, I think, the pandas UDF. So how do you tackle something like logging or error handling with that approach?
You are in the same, you have the same Spark logs, so because you use the same Spark context, and you keep it throughout, although you change language, it's eventually the same Spark stuff you execute, you just use a different API, so that still works.
Okay, so it's the same Spark session and you capture, for example, your log from that Spark session?
Yeah.
Okay.
Yeah. I believe so, yeah.
Okay. Thank you.
So I have a question that's a bit less technical perhaps than some of the previous questions.
Great.
keynote this morning started out quite ambitiously about wanting to conserve the planet and saving energy.
Yeah.
So do you have any figures on how much energy is actually saved using these appliances in homes?
How much is saved by using these appliances?
Yeah, by the insights that they give to the users.
So basically how we actually perform by giving these insights,
Yeah.
right? That's what you're asking.
Yeah, what's the impact on energy usage?
Yeah, so actually like our strategy here is to, especially for this use case, to really inform the user, so to give him insight, but we don't, you know, actively like say like, oh, go to Coolblue now and buy your new fridge, for instance. So that really, that activation, like literally making a change, that is left to the user. I mean, we can of course measure basically how the signatures of these appliances change over time. But yeah, I actually don't have active figures on that because that is not our core business. Our core business is to inform the people, not so necessarily measure what they did after that.
Right, thank you.
Thank you for your talk. I have a question about the anomaly detection part and two aspects of it. How anomaly detection.
What do you mean with anomaly detection in my presentation?
Do you track somehow the malfunctioning devices which have the pattern but they are a bit unusual, like twice as more as usual or something like that?
Yeah.
Or you deal with the malfunctioning sensors which just give the weird results and covering this?
Yeah. So first, so basically benchmarking a appliance and seeing if it's doing abnormal behavior. That we do because we have this whole population of appliances, so we can basically benchmark your appliance against other appliances and see if it's doing bad or worse. And also from industry standards, domain knowledge, we know what are typical good behaviors, and if you exceed certain thresholds, then we just give you the feedback in the app, hey, your washing machine is really heating up too long. That can either be because your washing machine is broken or you use it inefficiently. Then for the meters that are misfunctioning, because they're, for instance, the sensors are wrongly placed, this happens, but yeah, I mean, then we just don't get a signal and we actually via customer support have to get in touch with these people or either send, you know, a technical expert to repair that. That's not fully automated yet, as I know. Yeah.
Hello.
Oh.
I have two questions.
Okay.
Non-technical. The
Okay.
first question is, all this data you're collecting, do you sell that back to any of the utilities? Do you aggregate the information and provide any data back to the utilities providing electricity or gas? That's question number one.
I mean, we do give them aggregate reports on like how much users they currently have connected and so on. We are also, it's not like an active business right now, but it's starting up where we basically provide basically leads, for instance, which people, because we're also connected to the boiler, for instance, need a boiler replacement, and they should get in touch with for these kind of matters. So in that sense, yes, we also report back to the utilities because we really cooperate closely. We really like basically their technical expertise within their company in order to be able to serve such a product. Yeah.
Okay, sorry. And the second question is...
Second question.
Yeah, so you have all this PII data. I'm assuming somehow you anonymize this information so people's privacy is kept intact for
Yes.
GDPR. Okay.
Yes,
Just
we do.
curious. Okay.
Do you want me to elaborate on that?
No, I was just curious. Thank you.
Yeah, so in short, we have to treat all this data as personalized data because you see what we can do with it. We can detect behavior, these kind of things. And how we do it is like, basically the data is gathered just with an ID with none of the personalized stuff attached to it. And we have a separate, basically, table living somewhere else where we have the connection between basically this specific ID and which person it actually is or which household. Yeah.
Thank you.
We're unfortunately out of time. But,
Okay.
thank you for all the great questions, and thank you to our presenter. It was fantastic. If anybody wants to take questions outside or take it offline with the presenter, please do that. I think
so everybody who still wants to ask something, or there's also a bunch of colleagues of mine in the audience, so we can take it offline and have a discussion. That would be great.
And
Thanks.
Before we give a round of applause, just remember to please rate and review the session. So everybody, please make sure you do that. That's really important. Big round of applause, please. Yep.